All right, good morning or good afternoon, everyone. I will be talking about an ice giant pre-decadal study that was done. It was the first study NASA commissioned getting ready for the decadal surveys. Amy Simon and I were co-chairs of a science definition team for this study. I've listed the names up here of the full science team, and so it's all based on hard work from all these people and a team of engineers. But they have not seen these slides before, so any errors are their fault, not mine. All right, next slide, please. So our study was very different than the PMCS studies that you're hearing about this morning, in that our charter was not to identify a single mission to fly and a single point design, but rather to survey a broad range of missions. Missions to Uranus, missions to Neptune, missions to both planets, and at a range of cost points. And the idea was to prepare a report that sort of lays out a set of options that the Decadal Survey and NASA could use for guidance in picking what they want to do in the future. The full report was finished in 2017 and it's available online. You can get that URL by downloading this presentation from the OPEC website. The full report is massive. There's a lot in there. Last year, we published in Planetary and Space Science a summary that included some clarifications. So I encourage people to check that publication for as an accessible document for our study. In the previous talk, Abby already brought up the question of, well, if you want to go to an ice giant, should it be Uranus or Neptune? And as Abby said, our study, and actually the last two decadal surveys, both Vision and Voyages and the one beforehand, made the point that scientifically, each planet is individually compelling. And to first order, you can't rank one over the other. But the two planets are not equivalent. And as many of you have heard me say often, there are certain things you could learn only by going to Neptune, and there are certain things you could learn only by going to Uranus. So they are both of interest. Since Abby just presented a great discussion of some of the critical science that can be done by a Neptune mission, my job in this 10-minute presentation is to focus on the science that could be done if we go to Uranus. And so Scott, next slide, please. And I'll mention 5 items that I think are very significant. And perhaps the most significant to me has to do with the energy balance of the planet Uranus. So it is normal for giant planets to release more energy than they get from the sun. And this is because the planets, we believe, formed hot. So there's a lot of heat when a planet first forms, heat trapped in the interior. But also, even today, there's a release of gravitational potential energy as material from the outer layers of the planet fall in towards the core. That releases internal energy, things get hot in there. And so there's an energy source interior to these planets. And so Jupiter, Saturn, and Neptune all release significantly more energy than they receive from the sun. And that's because this internal heat, presumably by convection, perhaps even radiation, is brought outwards. Uranus is the unusual one. For reasons unknown, it is almost perfectly in balance and it's not releasing internal heat. And whether this is because the heat is trapped inside or somehow all its internal heat got released early on, that has profound implications for its evolution and what its internal structure is today. And so we'd like to see a planet that has these properties. And fascinating to me is the idea that perhaps ice giants naturally go through both sort of normal phases where their interior is convective and they look like Neptune and the other giant planets, but sometimes they go into a quiescent phase where the internal energy is trapped inside and the heat just builds up until at some point they explode in a flurry of activity. And so Uranus is our only example in that hypothesis to see one of these quiescent planets. So that's very interesting to look at. That lack of internal heat release by Uranus has implications for the atmospheric dynamics as well. Uranus is the only giant planet where the atmosphere isn't heated from below. So how does that affect the circulation in the atmosphere? Uranus also being tipped over on its side means the solar forcing is very unusual. And on an annual average, the poles receive more sunlight than the equator. How does that alter atmospheric dynamics? So Uranus is a unique laboratory for the atmospheric dynamics of giant planets. Similarly, Uranus is a unique laboratory for magnetospheric studies. Both Uranus and Neptune have extremely complex, fascinating magnetic fields. But Uranus, again, because of its tilt, its planetary magnetic field goes from being aligned with the solar wind to being anti-aligned and then back to being aligned every 17 hours. And I know this was discussed recently in a paper by Cow and Patty, where they referred to it as like a light switch turning on and off of the coupling between the solar wind and the magnetosphere. And Uranus has this unique forcing of its magnetosphere. Next slide, please. Regarding the smaller satellites and the rings of Uranus, on the right, this graphic sort of is a to scale drawing of the ring and satellite system of Uranus. Dashed lines are satellite orbits, and then the colored areas are rings. And in the interests of time, I'll just mention that there's a paper, I think it was Jack Lissauer and Mark Showalter, described the inner moons called the Portia group, which is kind of all around that red ring there, 8 satellites, as the most dynamically complex and chaotic spot in our solar system. These satellites are all coupled. We see changes in their orbits on decadal time scales, and they may be colliding on million-year time scales. Another fascinating thing is the outermost ring, that blue ring around Uranus, which is centered on the tiny moon Mab, sorry, I think that's proper. The properties of this mu ring, it looks just like the E ring of Saturn. And the E ring of Saturn is generated by the plumes coming off of Enceladus. But Mab is a tiny moon. It's only 10 kilometers across. So we don't think it can be active and having plumes. But there's this question then, how do you generate that ring like that that looks just like the E ring at Saturn?
Mark, 2 minutes.
Then the final science point I want to mention is the nature of the ice giant satellites. As Abby mentioned, when Neptune captured Triton. Triton is this fascinating object, but its capture totally disrupted the native satellite system of Neptune. So if you want to see what a large or mid-sized ice giant satellite looks like, the only place you can go is Uranus to see that. The 2 innermost satellites, Miranda and Ariel, Voyager saw that they show evidence of recent geologic activity, so they are geologically interesting. And some work has indicated that all 5 of the larger Uranian satellites are potential ocean worlds. So, well, okay, next slide, please. So I'll finish with this slide, and my 3 main points here are that Uranus and Neptune are equally compelling as scientific targets, but they are not equivalent. And I think Abby echoed this statement. And often, people may choose one or the other, but it has to do typically with their personal research interest and their own prioritization of the science. because Uranus and Neptune are very different, really, to understand ice giants as a class of planets, we have to go to both. But given that probably there's only one that will be targeted by a flagship mission first, it's probably going to be sort of programmatic factors that decide which planet gets visited first. So those are things like cost, schedule, risk, and then NASA looking at its whole portfolio of missions and the science it wants to do and the science it wants to emphasize. Striking some balance among scientific disciplines may also help decide which planet gets visited first. And with that, I'll stop there.